This video presents RCD-NB-01, a Level B study within the Radial Coherential Dynamics program. Its purpose is narrow and stated precisely. We characterize the non-equilibrium thermodynamic structure of the validated regime 3 coherence kernel. We do not assume apparent action. We do not derive geometry from the field. We do not address level C. What we do is this: construct a falsifiable thermodynamic characterization of an already validated stochastic process at the level of irreversibility and no further. The contribution consists of 4 sealed results and 1 open lock. Each result stands on independent footing. The open lock is registered honestly, not resolved. The object of study is a scalar coherence field C of x and t, taking values in the closed interval 0 to 1, evolving on a fixed Friedmann-Lemaitre-Robertson-Walker background. In its validated formulation, the field obeys a stochastic partial differential equation of Allen-Cahn type with Wright-Fisher multiplicative noise. The reaction term is a cubic double well, bistable with pure phases at 0 and 1. The noise mobility is state-dependent. It vanishes at the absorbing boundaries and reaches its maximum at the midpoint. On a radiation background, the effective diffusivity decays as d sub c divided by a squared of t. The reaction and noise terms are background independent at this level of treatment. The numerical integrator is explicit Euler-Maruyama, ETO convention. The dynamics are strictly parabolic, no causal cone, no signal propagation outside the diffusive envelope. To characterize the thermodynamic structure of the kernel, we construct its Itô MSR-Janssen-De Dominicis effective action. Introducing a response field and integrating over the noise gives the MSR-JD action. The noise vertex d of c appears in the numerator as a bounded polynomial, at most sigma squared over 8 on the unit interval. The action is well defined everywhere, including at the boundaries. The Onsager-Maclaup functional, obtained by integrating out the response field, places the noise coefficient in the denominator. For Wright-Fisher noise, this denominator vanishes at c equals 0 and c equals 1, producing a boundary singularity. The saddle point expansion of the Onsager-Maclaup form is non-uniform near the boundaries. The practical consequence: we use the MSR-JD action as the primary trajectory weight throughout this work. The Onsager-Maclaup form is retained only for large deviation arguments bounded away from the boundary. This is not a convention. It is the correct primary language for this noise structure. Result 1. Detail balance is broken by a structural mobility mismatch. A Markov process with state-dependent diffusion satisfies detail balance if and only if the corrected force is integrable as a gradient on field space. Equivalently, its functional curl vanishes. For the regime 3 kernel, the corrected force splits into a local reaction part and a Laplacian coupling part. The local part has trivially 0 curl. The Laplacian coupling does not. The functional curl of the corrected force evaluates to the effective diffusivity times a difference of inverse noise mobilities at neighboring sites. This vanishes identically if and only if the noise mobility is the same at every pair of connected sites. Since d of c is a non-constant function of the field, and the Laplacian connects sites with generically distinct field values, the curl is generically non-zero. Within the non-trivial Wright-Fisher noisy interfacial regime, this obstruction is structural rather than a parameter tuning artifact. To rule out a numerical artifact, a finite difference cancellation that might restore detailed balance on the lattice, we evaluated the discrete curl directly on the integrated radiation trajectory. Kill switch Cahn-NB-01, evaluated at the t equals 10 snapshot. 5,358 qualifying interface pairs. Median absolute curl approximately 5.09. Median to tolerance ratio 4.5 times 10 to the 13th. Fraction above tolerance 1.000. Green, the detailed balance obstruction survives discretization by 13 orders of magnitude on every interface pair sampled. Result 2. The active fluctuating sector is localized at moving interfaces. The bulk is thermodynamically silent, linearizing the SPDE around its 3 homogeneous fixed points, 0, m, and 1, and reading the noise vertex at each. At C star equals 0, D of C star is 0. At C star equals 1, D of C star is 0. At C star equals M, D of C star is sigma. Squared times M times 1 minus M divided by 2. Strictly positive, but the linearization there is unstable. In the pure phases, the noise vertex vanishes identically. The Gaussian correlation around the stable fixed points is identically 0 at every wave vector and frequency. There are no equilibrium level fluctuations in the bulk. Any perturbation is suppressed by the positive restoring rate, but no fluctuation is driven. The bulk is thermodynamically silent at Gaussian order. At the spinodal point, the noise is non-zero, but the linearization is unstable. The Gaussian description breaks down. Interfaces form. The active sector, the support of the medium functional, is therefore the moving interfaces connecting the two pure phases. This result is purely analytic. It depends only on the structure of the noise mobility and the propagators, not on any numerical measurement. It also justifies, after the fact, the interfacial mask used in RCD-NB-01 and in the medium functional estimator. The mask is not a numerical convenience, but an identification of where the active sector actually lives. Result 3. The sign convention and Stratonovich midpoint estimator of the T-odd medium functional are validated against analytic targets. 2 Ornstein-Uhlenbeck controls were run. Control A, a conservative one-dimensional OU process at stationarity. Detailed balance holds, entropy production rate is 0. The estimator returned plus 1.24 times 10 to the minus 6, statistically indistinguishable from 0. Control B, a two-dimensional rotational OU with non-conservative drift. The analytic entropy production rate is 2 omega squared over K, with K equals D equals 1 and omega equals 0.7, the analytic value is 0.98. The estimator returned 0.9800 to 4 decimal places. Together, these controls operationally fix the sign convention and midpoint implementation used in this paper. They do not resolve Spinney-Ford non-uniqueness in general. The multiplicative negative D prime over D term was separately audited against a transient analytic identity and converged under time-step refinement. Result 4. The trajectory level T-odd medium functional, measured on the bit-equivalent radiation coarsening trajectory, is negative throughout, with an overall magnitude decaying trend. The instrumented integrator reproduces the production trajectory bit for bit. Both gate audits pass cleanly. Integrated in windows of length 0.8, the functional ranges from approximately minus 1.3 times 10 to the fourth at early time to approximately minus 750 at late time. Negative in all 12 windows. Strict monotonicity is not claimed. A small reversal occurs near t equals 5.4. 3 pre-declared seeds were audited. The functional is negative in every window across all 3. The across seed mean decays by a factor of roughly 22. Relative spread rises from 1% to 29% at late time, consistent with fewer active interfaces and larger relative dispersion. A negative medium functional is not a second law violation. It is one term in the decomposition. The system entropy term is not measured in this work. Section 8. The open lock. A second law closure requires medium and system entropy terms summed. The system term is infeasible to reconstruct globally at this lattice size. We attempted a Fokker-Planck current diagnostic, inspired by lower bound constructions but not a rigorous lower bound. 4 closure conditions were pre-declared. The estimator returned approximately plus 207, reproducible across 3 seeds. Some face value checks looked favorable, including positivity of the diagnostic and inter-seed reproducibility. The closure was not declared green. 3 pre-declared failures. First, leakage. Mask retention averaged 23.8%, above the declared 20% threshold, capping the verdict at partial under R7. Second, sparse bins. The reported magnitude inflates with bin count, a denominator artifact, not a converged estimate. Third, condition 4 is null. The mask was nearly stationary, making the interfacial measure correlation uninformative. Verdict, partial, inconclusive. The value plus 207 is not a positivity claim. 4 results stand on independent footings. Result 1. Detailed balance is broken by a structural mobility mismatch. Analytic and numerically confirmed, surviving lattice discretization across 5 snapshots by 13 orders of magnitude. Result 2. The active fluctuating sector is localized at moving interfaces. The bulk is thermodynamically silent at Gaussian order. This is a structural consequence of the noise vertex vanishing at the pure phases. Result 3. The sign convention and Stratonovich midpoint estimator of the T-odd medium functional are validated to 4 decimal places against analytic Ornstein-Uhlenbeck targets. Result 4. The medium functional, measured on the bit-equivalent coarsening trajectory and audited across 3 seeds, is negative throughout, consistent with a relaxing, unforced process, with an overall magnitude decaying trend consistent with interfacial localization. One lock remains open. The closure of the total entropy production at the field level was attempted and returned partial. The system entropy term is unmeasured. The closure is identified as the natural next step. These results are stated at Nivel B, an effective, falsifiable thermodynamic characterization of the regime 3 kernel. They do not derive apparent action. They entail no emergent geometry interpretation. Their function within the program is delimiting. They identify which features of regime 3, the interfacial localization of irreversibility and the externally fixed T-odd convention, are structural to the coherence kernel. Any deeper description must inherit these features or account for departing from them. What sits beneath regime 3, if anything, is left outside the scope of this paper. That question can only be addressed once this characterization is complete.